All right. Welcome, everyone. Today is Wednesday. We are going to start or continue our paper readings, but in a much more open way. Till now, it has only been open to the participants at support vectors, in particular the bootcamp. Now I'm opening it to anyone who is interested. For your information, this thing is being live streamed to YouTube, to a public YouTube. So you are on record effectively. Now, the format of this is we will walk through this research paper. We'll understand its core ideas. It is one of those influential papers that led to a lot of downstream work in this field. After this paper reading is over, of course, if you would like to review it, you can go to the YouTube Support Vectors channel and see the video. Furthermore, for those of you who are part of the Support Vectors learning community, there's a bit of information. At some point tomorrow, you'll find that there is a page that will show up on the learning portal that will contain this video. It will also contain a complete summary of this session. Furthermore, it will contain some question answers that we are using, quite literally AI to generate. And finally, you will find a review quiz. Using the review quiz, you can check whether what you have understood about this topic is correct or not, or whether you need to go back and review it. So with those preliminaries, I will get started. This paper, Neural Discrete Representation Learning, came out a few years ago. And one second, folks, I'm getting a call. Hi, Madhu. We are live. Go to Meetup Support Vectors, Meetup link. Albert, could you please help Madhu? Yeah. Albert will help you. All right. Works. So this paper, Neural Discrete Representation Learning, it came out a few years ago. Now, it's hard to believe that so much time has passed since it came out. It addressed quite a few issues that we were having with variational autoencoders. And it led to a lot of downstream work. In fact, one can argue that DALI, the first version of DALI, if you remember, was not based on stable diffusion. The first version or diffusion model, was not based on diffusion models. It was based on a concept which roughly speaking is taking this idea of vector quantization of the variational autoencoder and putting it together with a transformer. Now, they did not specifically use the VQ-VAE. They used a variant of it. And I will discuss that variant also towards the end of this session. So I'm going to position this paper in a broader context of autoencoders and the things that it led to. So first things first, a very, very quick review of what an autoencoder is. Autoencoders are, in some sense, dimensionality reduction machines in the simplest sense. So for example, if you take an input, X, what you do is you transform it using some function, fx. You transform it into a latent representation or a hidden vector in belonging to a latent space, right? Let's say it belongs to a k-dimensional space, right? Or smaller dimension, let's take k-dimensional space. You reduce it to, right, a vector. And by the way, there are different kinds of autoencoder, but the typical picture of an autoencoder that you see, sort of the stereotypical picture, would look like this. You take an input, X, and there is the function, and functions, and as you know, the neural networks are effectively functions. So they will take this, and you will get a Z vector here. Z tends to be a lower dimensional space. So suppose this belonged to Rn. Typically, k is less than n, but this is not always so. You also have overcomplete autoencoders. So in other words, they may look like this. There are also autoencoders that look like this, in which just to complete the point, that k can actually be greater than n. But at this moment, to get an intuitive sense, just think about autoencoders as this thing. This is the autoencoder mental picture that you should carry. So if you think that fx, it leads to a latent representation, and then there is another function g, which acts on the latent representation, and it tries to produce an output, let me call it x hat. Now, the task that you train an autoencoder on is you say, excuse me, you say that x hat should be as similar to x as possible. Now, you can say, well, what's the whole point of it? You can just copy over x to x hat. That have a network that just does an identity copy. And when therefore, you can do an exact replica. But the point is, if you introduce a bottleneck, do you notice that we are saying that you're creating a lower dimensional representation? Let's say that the input vector is in 100 dimension, and here you're doing a 10-dimensional representation. You're taking data in a very high dimensional space and projecting it down to 10 dimensions. And these are nonlinear projections. So it doesn't mean that you just look at a linear. It's not principal component analysis, but a form of generalization of PCA. It is a nonlinear deformation of the input to a lower dimensional space, a latent space. This is your latent space. So you can think of autoencoders as a very encoders as an intuition as nonlinear dimensionality reducers with the caveat that, of course, not all autoencoders do the bottleneck. So this is the bottleneck. Some of them are overcomplete also. But we won't go into that for the time. Let's just stick to this, a more basic intuitive picture of an autoencoder. So it does a dimensionality reduction. Now, if you think of G as sort of and there are words for this, the f of x is the encoder layer or encoder network. The word function and network are sort of, in this context, we will use it synonymously. They mean the same thing, right? A network is effectively a function. And the GZ, so Z is equal to Fx, and GZ, which essentially tries to reconstruct is the decoder function, decoder network we can do. Now, these networks, as neural networks, they could be anything. They could be just linear layers, feed-forward layers. They could be convolutional layers. So as far as the autoencoder's basic architecture is concerned, you do have that degree of freedom to choose what you want. If you're dealing with images, then you tend to always take convolutional networks or convolutional layers as your encoder and decoder. So to encode, what you would do is, suppose there's a picture of a cat. You have a picture of a cat. Well, let's say that this is a cat. And you feed it into the autoencoder. Let's say you're doing that. Then it makes sense that you use convolutional layers. Conv layers. And you use these convolutional layers in the encoder. Is made up of the convolutional layers, and the decoder, right, and people often colloquially say that it deconvolutes, or it's sort of up resolution from a lower dimensional representation. It tries to come up with higher dimensional representation of the image. But the specific term is, these are transpose convolutions. Though intuitively, you can think of it as a form of deconvolution, though that would not be strictly true, but you can think of that. And in many ways, what you're doing is you're taking the convolution is trying to do this. It is creating from a picture, if you remember, this is just a quick recap, smaller, as you go and convolute over the image, you get smaller and smaller frames, right? But more number of channels, more features come out of those, right? You get a much deeper feature vector from that. And so at the end of it, you have a feature map, which is generally a much smaller number of space. Each of these frames maybe, so let us say that you have convoluted it down to, let's say 16 cross 16, each of these, but you will have a lot of layers. Let's say that you have created 512. I'll just take a number, features that you have extracted from the image, or 100, 128 or whatever, pick your number of features or channels that you have created from that image. Each of those channels, hypothetically, the idea is that the machine would have learned, the network would have learned some important characteristic about that picture, right, in each of its feature maps. So that is the convolutional aspect. And the transpose of the convolution is you take this information, these features that have been extracted, and from that you try to reconstruct the original picture. And therefore you can imagine that your loss is, one way to think of your loss as x minus x, right? How different it is. So you can take a squared loss, right? A loss term would be something like this, or you can look at it as probability of reconstructing S given Z. That's another way to look at the loss. Like, what is the Z you should create? What Z should be, latent representation should be. So you get high P X given Z. Probability of X given Z. You want to maximize the probability of reconstructing the original image. Right? So this is your reconstruction. This term is your reconstruction loss term. Term of the autoencoder. So this is a recap. Now, the next step in the evolution of autoencoders was, and there were many steps, but one of the crucial steps that came about was that in practice, what would happen is that in the latent space, if you look at the latent space here, there would be this problem that all the data, let's say that you're doing MNIST data set or handwritten digits and so forth, they would be like all over the place. They would not have very good structure, right? And some of them, they could be pretty much anywhere in the feature space. One of the problems with autoencoders was that if you make a sufficiently rich network, the machine may just learn to take each of your training data and store it at a separate place in the latent space, so that that point will reconstruct itself back to the image. Then the loss is very low. Reconstruction loss becomes zero, isn't it? And it comes from the fact that the feature space is the latent space is completely unconstrained in this loss term. It doesn't say anything about where the network should go position the point in the latent space, isn't it? So given that, it makes common sense that the autoencoder will figure it out that, oh, let's do one thing. Let's place all of these points in such a way that we can pretty much reconstruct it back. And just learn that if it is here, then it is this cat, this image. If it is there, it is this dog. So you can do that. So those were the problems of the classic autoencoder. So its solution was that you said that, no, wait a minute. What we want to do is we want to ensure that much of the data points, let us say, is centered around the origin. Let's say that you say it must be around, it must be highly likely around this region, right? Or much more prevalent around the origin and not so spread out. That could be a constraint that you impose. Now, if you think about it, that thing is sort of what you're saying is the distribution that this should have, the latent should have, let's say a distribution. It could be, for example, and this is what is typically taken, it could be a bell curve, a normal distribution. Are we together? It could be a normal distribution. A normal distribution is a generalization of a bell curve to higher dimensions, right? It's basically this. And this is the y-axis is the probability, and this is the location. Let's say that in this particular case, this is your origin, 0. And so what you're saying is data points are far more likely to be closer to the origin than far from the origin. That's a normal distribution. And when you impose this constraint on the latent space, then what happens is your loss term, and I'm giving you just the basic intuitive idea, the loss function for the autoencoder should now not only contain the reconstruction loss, but it should also contain a loss which says if you scatter data far away, there's a penalty for it, there's a loss for it, isn't it? So you can add up to a proportionality constant. You can say, I need to. And one of the simplest ways to do that was scale divergence. If you recall, in some of the prior talks, we talked about it. You basically say that, see, whatever distribution you are projecting data into in the latent space, Q, and the bell curve, we are imposing a distribution, a bell curve, a normal distribution. You basically need to make it look like a bell curve or a normal distribution, a multidimensional bell curve, or a normal distribution. And if you don't, then the divergence from that is a measure of the loss. Right? Now, KL divergence has a little bit of a property. It doesn't quite agree with notions of distance. Distances are supposed to be symmetric. KL divergence mathematically is not symmetric. So in due course of time, if you recall, Wasserstein distance took over and showed superior results, but we'll call all of this as variational autoencoders because these come under the class of variational autoencoders. But suffice it to say that you have now imposed a further constraint on the reconstruction loss. You said you can project the data. Neural networks can learn. The encoder can learn to project to a latent space, and the decoder can learn to reconstruct from it. But it must learn essentially to project data to look like a normal distribution. And when you force it to look like a normal distribution, then what happens is it cannot run too far away. And it sort of cannot memorize each of these points. Are we together? So that is the theory of variational autoencoders. Now, let's take that idea one step further. The problem that was there with variational autoencoder family, with KL, and I'm using the term more broadly with whether you're doing KL divergence term, Wasserstein, and so forth, there was a specific problem, and that problem was called, it is a collapse. The latent space gets completely ignored sometimes. So it is called, there's a very fancy term, and I'm hesitant to use that, but I'll use that, posterior collapse. Posterior collapse, right? So what is posterior collapse? Posterior refers to the Q this distribution here, the posterior. This is the language of the Bayesian probability theory. For the sake of this paper, I won't go too much into it because it gets a bit of a digression, but the posterior collapse, it has a very specific meaning. It means that when you create an autoencoder, then this decoder function, this G, ideally G should learn from Z and create the X hat, isn't it? X hat should be equal to GZ. But here are the ways in which it may not do so. Some ways are that the Z space is not rich enough to capture all the variety and variations of the input data. So input data may have color, texture, different genres of things, hills, rocks, cats, plants, and so on and so forth. And the latent space may not be rich enough to capture the whole information, content, of the input space, right? Or if you think of literature, then the input space may not be rich enough to capture the genres, the styles, the poetry, and things like that. It may not capture that. That is one problem that can happen. The other problem that can happen, and there are many ways that you can sort of land into this problem. This other way is that if your decoder is very powerful, it may just learn to memorize much of the input data, right? And so with very little hint from the Z, it will go and produce something, right? And it will produce something. So that is one. The other thing is that there's the posterior that you generate, the Z that you generate, is actually misaligned with the distribution of the input, the probability distribution of the input. It doesn't quite represent that very well. So there are many such reasons. And the other reason is literally, so you notice that the reconstruction loss and this, let's put a lambda term here. How much emphasis to put on the reconstruction loss and how much to put on the KL divergence, right? That's a degree of freedom you have when you're training your model. If you're not doing it well, you overemphasize one or the other, you can again have the posterior collapse, right? But how does it manifest itself? The way posterior collapse manifests itself, and this paper goes into it, is that, well, it doesn't, it talks about posterior collapse as a problem to overcome, is that whatever you produce will be rather bland. If you produce images, they'll be very generic images. If you produce text, it will look like very generic text. It won't have good flavor of the input. It won't have the genre and so on and so forth. It will look repetitive. Are we together? Right. So I can see you because I'm looking at the camera. You know. So all right. So that's a problem. So that's a problem of the posterior collapse, right? Means output is not as good, varied, etc., but is rather bland, and repetitive. Right? An example could be dealing with animals, and the only thing that always seems to come out are cats. Right? That would be an example of a posterior collapse. So with that context there, let us now come to, with that background in place, let us now come to this paper. So, well, okay, I would also give one more. Okay, I think we can talk about it as we go through the paper. This paper says, learning useful representations without supervision remains a key challenge in machine learning. So what does that sentence mean? Learning useful representations. What is the useful representation that we are talking about? Learning a good Z without supervision. Why is it without supervision? Because there is no label data. You give it, the data is there. You just have to learn a lower dimensional representation or useful representation of that data, isn't it? So X goes in and you try to reconstruct X. So it is, some people call it self-supervised learning and so on and so forth, such words, but it is without supervision, means without label data, without no label data. So that's the explanation. It remains a key challenge in machine learning. In this paper, so from that we conclude that at the time that this paper was written, people were facing the sort of issues I'm talking about. Let's say this. In this paper, we propose a simple yet powerful generative model that learns such discrete representations. So much is packed in this sentence. So let us unpack it a little bit. The first thing you notice is we propose a simple and powerful generative model. Where does the generative aspect of the model come from? What is generative about variational autoencoders? Remember, generative model. It comes from the fact that, see, if you learn the latent representation properly, then what can you do? You know that if all the points are centered around here and you have learned away, they are here, what can you do? You can randomly pick any point where data is likely to be. You know the posterior distribution. So you can go to a point in that any point in that distribution and ask the decoder to decode it, because you would know with a high probability that that means something. Semantically, it means something. So it will decode into a cat, it will decode into a specific kind of dog, or it will decode into a child with a particular face, or it will decode into music of a type or a text. Are we together? Because we know the distribution of the data specifically in the latent space. And so by knowing the specific distribution and by starting with the pricing, it must be like this. You get generative ability. And therefore, variational autoencoders are generative because all you need to do is from the sample from this sample, let's say you take an instant sample from this, any sample Z belonging to this latent space, and just pass it to a decoder, and you will get something exact, something realistic, isn't it? Therefore, once an autoencoder has been trained, a variational autoencoder has been trained, the beauty of this is it becomes a generative model, right? So that's the meaning of that sentence. And again, most of you who have been through all the paper readings, this is probably a 101 stuff and it's repetitive, but we'll continue forward. In this paper, we propose a simple yet powerful generative model that learns such discrete representation. So the first thing you get, your clue you get that something new is happening is a discrete representation. Because when you look at the standard variational autoencoder, the representation for each point, it belongs to a what? A latent space. So it maps an input to any point in the latent space. The latent space is a continuous space, isn't it? The only constraint is that the probability distribution of the latents should look like a normal distribution, isn't it? There are no further constraints. And of course, a bit more, I'm sort of glossing over some things. The probability of Z given X itself has to have a normal distribution like the structure, but basically they have to be normal, right? PZ has to be, they all have to be centered around this, around the origin and so on and so forth, or near the origin somewhere, and they have to be there. But within that space, all points are fair game, isn't it? It's an infinite space. I mean, any continuous space by definition has infinite number of points. So therefore, you can map an input to any one of these points. But what he is saying, or what these folks are saying, these researchers are saying, is something quite counterintuitive. It is saying that we propose a simple yet powerful generative model that learns a discrete representation. Now, you can say, now, wait a minute. You mean you're going to map all possible inputs, all the cats and dogs and horses and zebras and plants and trees and rocks to just a discrete set, let's say 10 possible points, 10 representations? A discrete representation is like basically a bunch of values. You have to pick it to one of the value, isn't it? And you're saying, wait a minute, how can that representation be rich enough to capture all the variety and complexity of the real data? That would be the question that would come to your mind, isn't it? And as we will see, it is actually possible. And in fact, it is quite intuitive, actually, that it is so. But let's hold that question in our mind. Our model, the vector quantized variational autoencoder, and VQ-VAE. And this paper obviously introduced the term VQ-VAE, which is why it's more colloquially called the VQ-VAE paper. It differs from variational VAEs, variational autoencoders, in two key ways. The encoder network outputs discrete rather than continuous codes. Means the encoder network will say, this cat, this, right? So if it is discrete, set of values, you can number the set of values, let's say from 1 to 100. And all you get is a choice that any input needs to be called any one of these 100 objects, isn't it? You have in other words, you have a finite vocabulary, of, let's say, 100 possible values in the 100 possible representations. You have to say it is one of these. It is almost like you're told that here is a forest, and whatever animal you find, you have a choice to call it a fish or a horse, like to take it to the extreme situation. Then you say, well, how will it capture all the variety and complexity of all the animals that I see? And you say, no, doesn't matter. Maybe I'll throw in a bird, a horse, or a fish. Whatever you find in the forest, go map it to one of these. Right? A discrete representation. Call it one of these.
So wouldn't it affect the output? Like, wouldn't the output be very limited?
Yes. So the whole question here in the audience is, won't the output be very limited? And the fact that it is not, just reading the sort of the abstract, it sounds counterintuitive. How would that be? Right? And yet this captures, as you will see in the experiment section, it captures a very rich variety of images and reproduces them with fairly high fidelity. But how is that possible? That's a mystery we'll get into. So, and then it says, so it differs from the variational autoencoder in two distinct ways. One is this part. The prior is learned rather than static. So we'll leave that. And the second is, the first is the encoder network outputs discrete, and the second is the prior is learned rather than static. So hold that thought in, we'll put it aside for the time being. In order to learn a discrete latent representation, we incorporate ideas from vector quantization. Using the VQ method allows the model to circumvent issues of posterior collapse, where latents are ignored when they are paired with a powerful autoregressive decoder. Right? So what are the latents? The Z's. So given an input, if it becomes a Z, you don't want the decoder to either completely ignore Z or to a large extent ignore Z. Now, you want it to maximally use the information content of Z, isn't it? Not do something from its own parametric space, the weights and biases that it has learned, and just go reconstruct something. Simply because it has in some sense memorized things that look plausible, right? So that's a powerful, typically observed in variational autoencoders. Now, what is vector quantization? Vector quantization is basically saying, I give you a small family of vectors. And whatever your input is, pick one of these. It's one of these. Are we together? Now let's take this idea a little bit more geometric. What you're saying is, what is a vector? Vector is a point in a Euclidean space, isn't it? So let's come back to the basics of math. Suppose you take this space, and I create a point, this point, right? This is the x1, x2. Let's take two-dimensional. So you would agree that this vector x is uniquely identified by the point's coordinate itself, x1, x2 value of this point, isn't it? And so therefore a vector is a point in a Euclidean space. These are equivalent ways of talking about it. If you can give the point, you can make an arrow from the origin to it. You have the direction and the magnitude of the vector. A vector is qualified by its direction and magnitude, right? So you have the vector. So think of vector as a point in a high dimensional space, Euclidean space, right? And so what you're saying, and so what it is saying is, if you do vector quantization, the basic idea is, let me make this line a little less. And so where I have some space here. What we are saying is every point x, first of all, create some vectors, which you call the embedding vectors. Let me call these embedding vectors E1, E2, E3, E4, E5, E6. Let me just say E7, and I'll just take 10 of these. Huh? E8, E9, And where should we place 10? For what it is worth, let's place 10, maybe here, E10, right? So now you say, if this is your latent space, this is your Z space belonging to, let's say, some dimensional space. Let's say K is equal to, well, in this paper, they use 512, right? Or no, they take 512D. Okay, we'll see what it is. It's been a while since I read the paper. We'll see what dimensional space they took, 64, whatever. Okay, I'll just leave it as some dimensional space, D. Right. So, but I'm taking here 2 dimensions. Now what it means is, suppose you have a point, what will the autoencoder function do? It will produce Z of X, right? Now, let me write the Z of X in a different color. It will produce, sorry, it will produce a Z of X. Z of X may land, let's say it lands here. Now, what you say is that if the encoder function landed Z of X there, you don't set that as the value of Z, latent representation. You instead find the nearest neighbor amongst the E vectors. So the E vectors, E1 to E10, they form your what is called the code book. Code book, by the way, is a word that's often used in computer vision, but I'll give you an intuition about it in a moment. But what you're basically saying is identify it as this, right? You say that X went and became E1. Are we together? It got mapped to E1. Now, you have to choose from this finite set of vectors. And every object will become one of these finite set of vectors. Now comes interesting thought, is that you don't map it to only one. In reality, what you do is you take different aspects of the image. Remember, when the convolution creates a feature map, lots and lots of and feature map, lots of features, right? So in the same way, what it says is you take grid. In this paper, they take a grid, but you can take it arbitrary of 32 by 32. 32. Each point, so you create for each image, imagine you create a grid of 32 by 32. And for each one of them, one encoder function maps it to one of the embedding vectors. So let's say that this point was mapped to E1, right? Another of these functions, F2, mapped it to E9, right? So you can just store you don't even have to store 1 and 9. You can just store the index of the vectors, E vectors, right? The quantized vectors. You can just say 7, 3, so on and so forth. You can fill it up. So you can come up with 32 times 32. Now, what is 32 times 32? It's close to 1,000, right? Isn't it? Close to 1,000, I think. Independent sort of mappings of the image to one of the encoding vectors. And in this paper, the number of encoding vectors actually they take is 512 in the experiment. So now you say, well, how many objects can it possibly represent? Because it's a finite representation, right? So how many objects can you possibly represent? Let's think about it this way. You have the first slot. So if you have 32 by 32, the first slot can be filled by any one of the 512 numbers, isn't it? Any one of the 512 vectors. So you have a choice of 512. The second slot can also be filled by 512, right? And so you realize that the total space of objects that it can represent, even though it is finite, it is a bizarrely large number. It is 5112 to the power 32 cross 32, isn't it? Because each of those slots, there are 32 cross 32 slots, and each of the slots can have any one of the 512 values, right? And if you realize what this number is, just to give you a sense, let me sort of exaggerate. 512 is approximately half of 10 to the power 3. It's in the order of 1,000, isn't it? And so you're talking about this to the power, well, give or take, this is 1,000, right? So you're talking about 10 approximately followed by, and I'm just doing hand waving arguments. You can correct me if I'm wrong, something like this, right? You realize that you reach 1 trillion by the time you go to 10 to the 10. You're talking of a bizarrely large number. So now you can rest assured that probably it can capture a lot of variety and a lot of information. The information space is very, very large, isn't it? So therefore, we don't need to worry about the fact that it's getting quantized, right? So that's a beautiful idea from which this whole thing emanates. So that's the quantization part it talks about. So if we get that part, the rest of the paper actually, I think we'll read pretty well. The whole problem is, the mystery is this. First of all, you have to imagine that fairy has come magically, taken the magic wand and told you that here are the 512 best points in the latent space. Isn't it? These are the 512 best vectors. How did those vectors get discovered? Like in the beginning, just imagine that somebody magically, God-given, a fairy came, just says, here are the best vectors. So your problem is half the problem. All you need to do is train an encoder to map each input to one of these vectors, isn't it? And so what can you do? You can have, so let us think in terms of the loss function. The loss function will have, let me use a different thing. The loss function should have the reconstruction loss term, reconstruction loss term, right? Which is more formally log x given z, like whatever latent space you create, out of that you have to reconstruct x. But how far you are from x, like you sent in a cat and a dog came out, you're pretty far, isn't it? So how far you are, that is your standard reconstruction loss. Right? So that term will be invariant. We'll leave it there because that is baked into the definition of an autoencoder. But you need one more term. You need to make sure that your z, where it lands pretty close to one of the vectors, EI, the closest vector, right? So EI is the closest codebook vector or vocabulary vector, if you want to think of it, to Z, right? So this is the divergence. This is the gap between the vector. What is a good way? There are many ways of looking at the distance between two vectors. The simplest is, of course, just take the L2 norm, isn't it? The quadratic, the Euclidean distance. Just take that. Does that make sense? And would you agree that if you can train the network so that it more or less maps inputs to one of these, right, code vectors, the more it aligns to the perfect code vectors, the better, isn't it? Because ultimately, the decoder will not get Z. What will the decoder get? It will get EI, right? So remember the journey. So let me reconstruct the journey. A point X goes in through this function fx. It lands at Z. It lands here. But there is a nearby, there is a EI, right? So what do? You replace Z. Z gets replaced with EI as the value for Z, isn't it? That vector. So what goes into the decoder? Decoder function will decode EI, the quantized vector. Are we making sense? Right? It will go with that particular term. Now comes an interesting thought. This is what the encoder is doing. Because this goes in, and if Z is very far from EI, it means like even the closest EI is pretty far from it, means what is coming into latent space and what is going out to the decoder are far, they are different. So one would imagine intuitively that they would lead to divergent results. It wouldn't look like X. The decoding of EI will not look like X, isn't it? And so you want to minimize that. So this last term makes, I hope, very obvious sense, isn't it? It should make a pretty obvious sense, one would imagine. And in this paper, there is I think there's a bit of terminology that is associated with it. So this is your, this particular loss term in the language is called the commitment loss. Why? Because given Z, you committed to EI, the nearest code vector. And by instead of sending Z to the decoder, sending EI, you have taken a loss, right? That is your commitment loss. And that, of course, as you see, is this. So this term makes sense, isn't it, guys? Right? But there is a problem. How in the world? Well, in this world, we don't usually, when we train a neural network, we don't quite invoke a fairy to come and tell us the best the best code book of vectors, isn't it? So now we need to do one more learning. We need to learn the best code book of vectors. That remains also to be done, isn't it? So what you do is you jointly learn. This is a beautiful thing in this vector quantization thing, that you jointly, you make small learning to align the Z to the code vector. And so what you do is, when you're doing the commitment loss, remember, this is fixed. So these people use a terminology. They call it, the gradients get frozen. So you will see SG. In the paper, they use the term SG. SG-EI. Whenever you see SG, it's just a frozen gradient, static gradients. Means it is not going to change. When you're doing the gradient back propagation and gradient descent, you're finding the gradient, this term will act as a constant. Why? Because the codebook vectors, as far as this loss is concerned, commitment loss is concerned, is sort of God-given to you, right? You're trying to align Z to and assuming that the code vectors are in the right place, isn't it? The perfect code vectors have been given to you. So the code vectors, therefore, are constants, isn't it? So when you take the gradient, the gradient with respect to the code vector will be 0, isn't it? That is the meaning of the term SG that you find in the paper. The loss function is equation number 3 in the paper, you will see. And so let me go through that. Let's go through this paper a little bit more now. We'll come here. So we will skip over a related work of what other people have done. Let's go straight to their thing. Perhaps the work most related to our approach are variational autoencoders. So this is it. We define, so this is the point. We define a latent embedding space E belonging to K, where K is the size of the discrete latent space, i.e. a K-VAE categorical. So K is 512. In this, when they did the experiments, they took K as 512. And D is some dimensional space. We can go down and see what that dimensional space is, but take a sufficiently large dimensional space, right, for the autoencoder. Let's say 128 or something, some dimensional space. Note that there are K embedding vectors, each belonging to a D-dimensional vector space, isn't it? So those God-given vectors given to you are the EIs. As shown in figure 1, the model takes input X that is passed through an encoder producing output Z. So far, so good, guys. The discrete latent variable, so Z are then calculated by a neighborhood method. So now the question is, if you take you take the FX, it will land somewhere, right? It will land somewhere, but it will land here. But you don't take this as your Z. Your latent representation, you take as Z. So this he calls ZEX, right? But you take the nearest code vector to it, right? Producing is passed through an encoder, producing output Z. The discrete latent variable Z are then calculated by a nearest neighbor lookup using the shared embedding space E, as shown in equation 1. So guys, this makes total sense, isn't it? You say that Z is that particular K that particular vector that is closest to it. Argmin means where are you closest to? So that is good. So where Z is the output of the encoding. So ZE is replaced with Z. Z happens to be given by this, which is the Z is that particular E. Let me call it EI. So that's the whole point. Now, I will skip over some of these things. We view this model as a variational autoencoder in which we bound the log P, the prior distribution of the input, with the elbow, right? Elbow comes from a Bayesian, variational stuff. It's a variational term. It stands for expectation lower bound. Right. Now, it's a bit of a mouthful. I don't want to go into the Bayesian theory at this moment. So we will sort of gloss over this statement for now. Right? A proposed distribution Q is deterministic and by definition, a simple uniform prior over Z. So see, what they're saying is that our proposed distribution means they are saying that C is deterministic. All you have is some fixed distribution of the input over the categorical values, right? And so, for again, is the Bayesian term. The KL divergence is a constant. The KL divergence is given by it is something like a Q Z of X log Q Z of Z given X right? Divided by, I believe the term should be PZ. Right now, all of these, you see here, what is Q? It is very fixed. It is 0, except that it is that particular vector. It's not a distribution. It is very clearly this particular vector EI, right? And so this entire term becomes a constant term. Right? So we leave it as that. And so it goes back to the variational autoencoder theory that the KL divergence term there disappears and we ignore it. Instead, it gets replaced by the sort of terms we are bringing in. Now, what is the learning? How does it take place? So let's look at this equation number 3. It is telltale. The first term, as you can see, is basically your reconstruction loss, right? Reconstruction loss that we have been talking about. Like how close is X hat to X, isn't it? The output, how close is it to the input after being reconstructed? That is the term. So that is the classic autoencoder term. Now, what is this term? This is the last term. It is saying SG. Wherever you see SG means think that at this moment the vectors are frozen. The embedding vectors, the codebook vectors are frozen. You're not changing them, right? They're God-given. You're not learning in this term. You're not learning those vectors. They are frozen. But you're learning the results of the autoencoder. ZEX is basically the output of the autoencoder. It's basically Z is equal to FX if this autoencoder function. If X goes in. So you're trying to align. This is basically, you land here. This is ZE of X. And here tends to be a QI. This gap is your commitment loss, right? Because you're going to say, no, Z is actually equal to EI. No, I shouldn't say QI. EI is equal to EI, right? It is this particular nearest neighbor vector, but it is not. There is a gap between the two, and that is the gap that this term in the loss will try to minimize. Now, what about this other term in between? What in the world is this term now? what is this term? So what it is saying is, this term says that, okay, let us assume that the ZE where it lands, the autoencoder is correct, right? The autoencoder is whatever it is doing, let us assume that it is correct. And it landed in the right place. But the nearest neighbor vector, right, is not in the right place. Let's move the nearest neighbor vector, the codebook vector, nearer to it. Do you see how it is? This term tries to move ZEX towards a EI, the third term. Tries to, does that, right? It pushes ZE closer and closer to the nearest vector. But what does the middle term do? Remember, I said that in the beginning, assume that a fairy has just given you the perfect code book. But that's not true. In reality, you have to learn the code book, right? And so how do you learn the code book itself? It is through the middle term. And this middle term is your code book. That's why it's called the code book loss term, because it is learning the code book itself. This is the code book loss. And this is the commitment loss. That's the intuitive meaning, because see, let's look at this term. What are you doing? Your SG, the word SG is in front of the ZE, this term. You're saying, assuming that the encoder is correct, what do I need to do to the code vector, nearest code vector? I need to use gradient descent on that and bring it closer. Closer to where it landed. So you're making improvement on both sides. One term is taking the code vectors as God-given, as fixed, and moving the point to the nearest code vector, closer to the code vector. So it is actually modifying the encoder. Remember, the third term is going to end up changing the weights and biases of your encoder, isn't it? And of course, the first term will, of course, do that, but both the encoder and the decoder. But the middle term, what does the middle term do? Does it touch the encoder? It doesn't touch the encoder. It instead moves the codebook vectors. It learns the codebook vectors. Guys, are we following this?
The middle term is basically choosing the right quantized point.
Exactly, choosing the right quantization vectors, right? Choosing the right codebook. That's what it is doing. Now, one question that arises that, what are the, like, intuitively, yes, it makes sense, but does this make sense? Like, is it how nature works, or are there any other analogies to this? So think of it this way. See, I'm speaking. Whatever I'm saying is ultimately audio waveform. It's a continuous waveform, right? But theoretically, you can project it into a continuous space. But in reality, you can break my words, everything that I'm speaking, into linguistic pieces called phonemes, sounds, pieces of sound. And those phonemes are finite for the English language, for example. Right? You can break the word break, right? It's a phoneme. R, A, K. These are phonemes. You can break it into its phonemes. But the set of phonemes is finite. It's a quantized vocabulary, isn't it? It's a code book. The phonemes of sound are the linguistic code book for speech, right? Likewise, for the written word, what you typically do is you take a finite vocabulary. For example, whenever you do train AI models, often you take a vocabulary, let's say 30,000 words. What are you saying? That the input can just map to one of those words. But using those one of those words, you can reconstruct, again, a very rich variety of text, isn't it? So if you think, if I allow you, here they said 32 by 32, which is approximately 1,000. So if I were to say, you can write an essay, forget about grammar, write an essay using this 1,000 of 1,000 words from the dictionary. Like you cannot make up your own words, but you have to pick the words from this dictionary, from the English dictionary. Well, you would realize that this is a pretty vast space of essays that can be written, isn't it? Now, once you impose further structure like grammar and so on and so forth, it will reduce the space, and yet it's a fairly vast space. I don't think that every possible essay in English of 1,000 words has yet been written. That is grammatically correct. So these are large spaces. So you can see that there are real life examples where quantize, you use a code book. And this is the main point of this paper. Now, there is a bit of technicality that goes into this paper. So let's look at this diagram, which says a lot. So you have a dog on the left, right? Here is a dog. This is your X vector. Right? You can make it into X vector. This goes into your convolution layer, CNN. What will it produce? It will produce ZE of X, right? It will produce a embedding vector. But that embedding vector, you need to find the nearest codebook vector. So here is your codebook vector. Codebook of E1 to EK, K here being 512. You have to pick one of those 512 and say that it is one of them. Are we together? Right. But then you don't do only one. There are other features that you extract from that. It maps to another vector, it maps to another vector, and you come up with this 32 by 32 a brick, right? You come up with 32 by 32 a brick, right? And then of course, because there are many, each of these is the d-dimensional vector. Remember that these quantized vectors are d-dimensional vectors, right? D-dimensional vectors. So the total space will be this thing, d-dimensional, and this. And now comes this thing. What does the decoder get? The decoder doesn't get the original vector, the Z, the latent vector. It instead gets the nearest codebook vector. It gets an index. Let's say it gets 3. Pick up the third vector from the codebook and decode it. And it basically gets this map. From this, it will go through the decoder and it will create this particular thing. So now let's think, how will the gradients propagate? Because you have to learn a good code book and you have to train the encoder and the decoder as you would do for any autoencoder. So up to the decoder part, the gradient descent and backprop is fine. But there is a problem with this whole business of ZEX being replaced with some EI, which is nearest EI. Right? The problem that happens here is the gradient just vanishes. Why will it vanish? So here, take this point. This is EI, right? Let us say that ZE of X landed here, and this is the closest EI, right? What will happen if I move this a little bit closer? I come here. Will your loss change? You're still picking EI, right? If I move it a little bit closer, you are still picking EI. Means once you come in the neighborhood of EI and other points are more distant, coming closer, learning better ZI is not going to help you, isn't it? You're not getting any better. Your loss is not going to is not really responding to this changes in the Z at that particular moment, isn't it? So there is a bit of a thing that you have to do. You have to be a bit clever. So what you do typically is the gradients that come up to here, you just do this. You see this red line here? You just say, hey, these things live in the same space. Now, these gradients are living in the same space as the vectors, because this embedding vector and the Z vector, they are in the same space. So the gradients are in the same space. Let's just copy it over. Right? Copy it over, and it sort of makes sense. You're saying that while I'm learning the encoder part, remember there's one term that is the encoder part, I will pretend as though there is this code page vector choice is not happening. Right? It is as though if I just copy it, if I just copy it over, then for that part of the learning, you pretend as though this whole quantization is not happening, isn't it? For those gradients. You're saying, okay, you did backprop of the decoder, now go do backprop of the encoder. You said, now wait a minute, but then haven't we rejected all the code book? No, because that information is there in this part, right? And it will show up in this part, the second part also, right? The second thing that will happen is there is, in this second term, the codebook loss, you are actually doing a gradient with respect to the codebook vector itself. You are moving the codebook vector, the E vectors, right? The E's are moving around. So you sort of have a bypass path, and then you know that you can do it because you also have a path of moving the vectors around, right? And so it works. It does work. And that is the gist of this paper, right? And then there's a little bit more to it. The second contribution is the prior distribution of the latent is a categorical distribution. So now you realize that you have only 512 choices. So if you look at the distribution of data over this space, latent, it's a categorical. So see, for example, if I give you a room full of cats and dogs, then you can only come up with something like that, 100 cats and 20 dogs. Something like that, right? And then from that, you can normalize and get a probability of cat and dog, right? Suppose this is for cat, this is for dog. This is discrete distributions, right? So that's what it means. So it says that over a discrete latent is a categorical and can be made autoregressive by depending on other Z in the feature map. Or while training the VQ, the prior is kept constant and uniform. So you keep the prior constant and uniform. Uniform saying that all of them are equally likely. After training, we fit an autoregressive distribution over Z, PZ, so that we can generate X, Y ancestral sampling. And there's a pixel map that can do that. So basically you learn it, whatever. So now they go into the experiments, and that's where they mention what the values they take for that. We trained these models using standard VAE architecture. Encoder consists of 2 stride convolutions. So the stride is 2 with window size 4 by 4 following 2 residual blocks. ReLU is their activation function. 3 by 3 convolutionals, ReLU, 1 by 1 convolution. So they keep going down, all having 256 hidden units. Right. The decoder is similar, has residual 3, etc., etc. We use Adam optimizer, which obviously still its variants continue to dominate and be pretty commonly used, with a learning rate of 2 e to the 10 to the minus 4, and you evaluate the performance after 250,000 steps with a batch size this, right? Now the images are taken as 128 by 128 by 3. 3 is the RGB, I suppose, space, by compressing them to a Z. So the Z space, as I talked about, is 32 by 32 cross 1 discrete space via purely deconvolutional PXZ. So a reduction of blah points in a bit. So these things will skip over. Somewhere it says that K is, here it says, with a K of 512. Right? Now, if you look at the experimental results, look at this vertical line. This is data input. This is the reconstructed output. Observe that the input has a pretty large variety of things in it. Oh, there's a dog, there's a boat, or is it a boat? Yeah, it looks like a boat in the water. There's a land, there is an animal, there's a binocular, pencil, paper, etc. And you're asking the VQ-VAE to decode, to reconstruct it. And it seems to have done a pretty good job of reconstructing it, isn't it? Like with very imperceptible loss of loss, it seems to have done it. So it is pretty remarkable that it can do it. That is why it got a lot of attention. And when you sample off this to generate images, it tends to generate pretty realistic and varied images, isn't it? And you can do the same thing with audio. left original waveform, middle reconstructed waveform, right? And right is reconstructed with different speaker D. So one of the things you can do is, and again, this happens. I am saying something, but I want it to come out in the voice of, let's say, some other speaker, hopefully a much better speaker. So you can do that, right? You can, because it's a generated model, you can try to do. So this is the open to style transfer and so on and so forth. So you can play with audio, you can play with video, and so forth. So anyway, guys, we had a pretty good, hopefully, an hour of it. I will like to open it up to questions. Any questions, guys? Was this clear, by the way? Any feedback? Everybody is very quiet here. Was this reasonably clear?
Absolutely.
Good. Any questions or anything I should clarify?
Asif, I have one question. So if you could go back to that method that they were applying, the formula, what is that 2 by 2? I was trying to understand that a little bit. If you could go down in the paper.
Discrete. You mean the loss term? No.
Yeah, there's a function. You go down. Yeah, right there. I'm sorry, right there. This one right here. Sorry, you're there.
Okay. So which sentence?
Loss. Yeah, you see that 2 by 2. What was that 2 by 2?
Is it above the? Is 32 by 32?
Oh, got it. Okay.
Remember, I told you that they create basically a grid of for images, right? Each of them is, so basically this is your, like, think of it. It's like sending your message, words. You have written, these are the words that you wrote in a grid. That's that.
Got it. It's a matrix. Got it.
Yeah. And each cell in the matrix is basically the index of the vector that is nearest. One of the a value from 1 to 512, I suppose.
Got it. Yeah, this is where that large number comes in. Got it. Thank you.
Of course, this is what they took. Of course, people may choose. There is no specific reason why you chose this. They just empirically found that this works and they used it. Subsequently, it would be nice to find out what people are doing nowadays. What's the code
I have
book?
a question actually.
Okay, go ahead.
Yeah. So in this case, I saw that half of it could be reconstructed exactly.
Yes.
Will it work in image transmission for one place to another completely? Will that work here, or can it be used?
It does actually. It is so you're looking at it as a form of minimally lossy compression and transmission. Yes, autoencoders have been used. I don't know to what degree of success. I think Dilip here is from information theory background, can tell more how prevalent it is to use it. But deep learning people obviously look at it as a pretty good way, a pretty powerful way of data compression.
Okay, thank you.
Yes, you're right. Vector quantization and vector code books are very prevalent for speech and video compression and all that. So this would naturally translate to that. So
Another question I have, Dilip. So will this bring back because the metaverse concept? Because the problem here is that the transmission speed is very, very slow nowadays because the compression algorithms have been exhausted to the nth degree by the GPU level 4090. So will this make some difference there? Just open question.
So,
Um,
you're asking about data compression, right? I mean, uh, to
So
you
data
will,
compression to transmission, right? So what happens is the data goes into the GPU, then basically it has to be transmitted over the wire using the compression there. And on the other side, the other GPU reconstructs that and showcases that. The current problem in this metaverse concept thing is that realistic deconstruction and reconstruction is not possible at because you have 30 frames per second. So it's not really possible to do realistic on the wires. Current hardware doesn't support it. But
yeah.
if we find some software breakthrough, so that to minimize that, again, I'm thinking about will this paper cause that kind of difference or not yet? We are not there yet.
No, so like Asif was saying, as you try to encode, you use a finite code book because you actually have diminishing returns. Beyond a certain point in the vocabulary, the words are not going to be used, and so you cut off at that point and map all the remaining words to a single word kind of thing. And so your compression is limited to that to the codebook size that you use, and that is dependent on the frequency distribution of all the words in that codebook. And if it spreads out further, if in space, to say 30,000 or something rather than 1,000, then you have a large space still to kind of encode. And so you're limited by that, by the size of the code book that you have to use to represent the information without uh, without much loss, right? With very little loss. And Asif has been talking about that in the past, about how to do that in these um, the latent space embedding would be limited to to at least having sufficient size to represent the information without loss. So um, then beyond that, you can't do much more compression beyond that. So
Okay.
so there are two things: There's source coding, right, that limits this kind of space, and then there is also you have errors during transmission and then you have to correct, and so then you have error correction to correct for that if you have any packet losses or bit losses over a wireless channel, things like that. So combination of source coding and channel coding is required. Source coding tries to compress, and channel coding actually expands the space a little bit to add redundancy, and overall you try to get end-to-end good performance. So and you're limited by that size of the codebook that you will choose to represent the information for minimal loss. So yeah, there's not much you can do beyond that. So it depends on what information you have, right? And so regarding metaverse and all of that, it's a lot of data that you have to send. And so hardware capacity, as you get more and more parallel hardware, you should be able to start doing those things in real time. So I think it'll get there eventually, but also energy becomes a problem.
Okay. Thanks. Yeah.
Any other questions, guys?
So the question that I have is regarding the various keys that we select.
Yeah, the code book, the vectors that you selected.
Yeah, so the thing is that so the thing that I'm still not clear is like, we spoke about this 32 grid.
Mhm.
And then we are having a specific key for each grid.
Yeah, each cell. So basically in each cell, you need to write which vector, which of the embedding vector it is. Oh, 11th one. Oh, 16th one. Things like that. That's it.
Okay.
So what you finally, the latent representation is literally a grid of actually numbers, integers. Indices,
Indexes of the-
indexes, exactly. 32 by 32 grid of indices. Any other questions? All right, folks. So then I'll close today's session. I'll stop the recording too. Remember, folks, this is live streamed to YouTube. If you go to youtube.com/supportvectors, you will find this recording there. And furthermore, those of you who are participants at Support Vectors Bootcamp, in a day or so, you'll find a page on our learning portal. You'll see a section in which this paper is discussed. But more than that, we will be doing augmentation, a summary of everything that I said. The main key points will be generated and mentioned, written out. Some question answers will be written, like for you to check out your understanding of the paper, and there'll be a small quiz that you can play with. So these are sort of just ways to review if that interests you. Thank you, guys. And have a pleasant